So this is 947, and we're looking to determine the current. So what we want to do is find the equivalent impedance here. So we have the voltage source, and we could write the voltage source as 115 at 0 degrees. And we know omega is 2000, right here, 2000. Now, let's look at the impedance of each of these. So the impedance here is an inductor, and that is equal to j omega times L. And that is going to be j times omega, which is 2000, times L, which is 2 millihenry, which is 0.002. So this value comes out to be, that is J4. So J4 here. And then we have our resistor, and then we have our capacitance, which is 1 over J omega C, which is also equal to negative J divided by omega C as well. So if we do that, that is negative J divided by 2000 divided times 50 times 10 to the negative 6, because this is microfarad. And if we do that, we have 2000 times it should be 10. So this comes out to be negative 10, or negative J10. Okay. So let's move this to the frequency domain, and I'm going to redraw this circuit. So this is the circuit. So we have 2 and we have 20. This up here is J4, and this over here is negative J10. And this is 115 there. Okay, so we're in the frequency domain, and we want to figure out this current I. So to figure out this current, we need to combine things together. We need to figure out the equivalent impedance. So these two are in series. J4 and 20 are in series. So we can add those two together. That's 20 plus J4 for these two. Now, these two are in parallel with this. So let's take this and put it in parallel. So we take this times our negative J10 divided by 20 plus J4 plus negative J10. Now on the top here, that is negative J200 minus J squared times 40. And then on the bottom here, we have 20 minus J6. So if we remember that J squared is equal to negative 1. So simplifying this further, that comes out to be looks like 40 minus J200 divided by 20 minus J6. Okay. So let's simplify. Let's put these in polar coordinates. So 40 minus J times 200, J200. Let's see, R is going to be equal to 40 squared plus 200 squared squared plus 200 squared. So that is 203.96. And theta is equal to the inverse tangent of negative 200 divided by 40. And that is equal to negative 78.69 degrees. Now let's do the 20 minus J6. R is going to be equal to 20 squared plus 6 squared, square root of that. 20 squared plus 6 squared. That is 20.88 there. And theta is going to be the inverse tangent of negative 6 over 20. Which is negative 16.70 degrees. Okay. So let's keep going. Subbing these in, this first top part, we have 203.96 at an angle of negative 78.69 divided by 20.88 at an angle of negative 16.70. Okay, so that comes out to be 203.96 divided by 20.88. That is 9.768 at an angle of 78.69 plus 16.7 at negative 62 degrees. So now that we have this answer here, let's convert that back to our Cartesian coordinates, or our real and imaginary coordinates. So we have the real portion is 9.768 cosine of negative 62 degrees. And then plus J 9.768 sine of negative 62 degrees. And if we do that, calculate that quickly. 9.768 cosine negative 62 degrees. That is 4.58 or 4.59 plus 9.68 sine negative 62. That comes out to be a negative number, so let's put a negative. Negative J 8.62. 8.62. Okay, so let's grab that. Let's take a look. So that is the combination of all of these resistors together. Now we need to add the 2 to it. So the total here is, this is our total impedance. The equivalent impedance is equal to this. All right, so now we can move on to finding the current, I. So we have the voltage, and we just need to divide the impedance to find the current. So let's go ahead and let me grab another sheet of paper. Go here. And so we have the total impedance. And then we have our voltage source is equal to 115, 0 degrees. Now let's convert this to our rectangular or polar form. So R is equal to 6.59 squared plus 8.62 squared, square root of that. We have 6.59 squared plus 8.62 squared, square root of that. That comes out to be 10.85. And then we have theta, which is inverse tangent of negative 8.62 divided by 6.59. And that value is 8.62 divided by 6.59. That is negative 52. Negative 52.6 degrees. So our equivalent impedance is 10.85 at an angle negative 52.6 degrees. So our current I, which we're trying to find, is the voltage of the source divided by the equivalent impedance. So the voltage source is 115 at 0 degrees divided by our impedance, which is 10.85 at an angle negative 52.6. So by doing this, we come out, and that is equal to 115 divided by 10.85. We have 10.6 at an angle of 52.6 degrees. So if we write that as a function of time, that is 10.6 cosine of omega, which was 2000 t, plus 52.6 degrees. That is in amps. So this is our solution for the current of the circuit.